Okay, for DC circuits, right? We have already learned some of the things, so it's not going to be completely new. Okay, it's not going to be completely new. Right now, we have learned, right, in the in the previous chapter. Okay, if we move up here, that V equal V1 plus V2 in a series circuit, and V equal to V1 equal to V2. That means V is constant in a parallel circuit. Okay, right? It's like you can think of it this way. Okay, for series, okay, it's like if it's a Wild Wild Wet, the kind of slide, right? Okay, the series is like two slides added together, V1 plus V2 is equal to the EMF V. All right, it's like the battery sets up the EMF of V, and then there are two components that use up the energy, right? Energy to drive that unit charge through the component is the PD, right? So series is like this. Parallel, you can think of it as the slides. Okay, the EMF is still V. Okay, then there are two slides, but now the slide is side by side instead of one on top of the other, right? Because they're parallel, right? So parallel V1, V2 are all the same. Okay, so for series, V is equal to V1 plus V2. For parallel, V is constant. Okay, right? So this is what we have learned. Okay, so if I were to draw the circuit again, okay, let's say we have a resistor this time. Okay, we call this R1 and R2. Okay, so if I have I draw the voltmeter separately because it is not part of the circuit, right? So I'm going to use another color to differentiate, okay, to differentiate the PD, right? Okay, I'm going to draw it on top here because I don't have space, doesn't matter. Okay, R1 and R2. Oops. R1, R2. Okay, then I will put, I'll add I inside here. Okay, so it's series, then parallel. I'll just draw two resistors in parallel, but it can actually go on. There can be R3, R4, R5, but I'll just draw one R1 and R2. Okay. R1, R2. Okay, now there are different currents. So current I is the main current in the circuit. And then I1 is the current in the first branch. I2 will be the current in the second branch. Okay. And then we have the voltage. Okay, for the EMF, I call it V. For the PD across resistor 1, we call it V1. And the PD across resistor 2, we call it V2. Okay? So let's now write down the three equations that govern this series and parallel circuit. Alright, so I'm going to write again. This one is series. This one is parallel. Okay, so the three equations will be, for series, current is constant. Okay. V EMF is equal to the sum of the potential differences. All right. Okay, and resistance, effective resistance, okay, total resistance or effective resistance is equal to the sum of the resistances. Okay, I will explain to you where this comes from. All right. Then for parallel circuit, current I is split up into two or more paths. Right? It's like a river that split up into two smaller rivers or streams. Okay, so I is equal to I1 plus I2. So when we say electric current, okay, water current is a bit like electric current. We can use that analogy. So the big river is split into two smaller rivers. So the sum of the two smaller rivers, the amount of water will still be the same as the original river, right? So I equal to I1 plus I2. Then V is constant. As we have mentioned just now, V is constant. So V equal to V1 equal to V2. Okay, V is constant. All right. And resistance, okay, this one is a bit different. The effective resistance, 1 over effective resistance is equal to 1 over R1 plus 1 over R2. Okay, if there are more resistors, then we add plus 1 over R3 plus 1 over R4. Okay, but here there are only two branches, so I just write 1 over R1 plus 1 over R2. Okay, can? All right, so this is the summary. Yeah. Okay, maybe I'll just write, this one is for parallel, equation 1, 2, and 3 again, okay? Okay, later, let me explain first, okay? How did we get these, all right? So, how did we get these three equations first, So, let's start with a series. Okay, series. Okay, how do we get R equal R1 plus R2, okay? We start off with V equal V1 plus V2. This one we already established earlier on. In a series circuit, the sum of the potential differences is equal to the EMF, right? The EMF is not V1. The EMF is V. Okay? So, V equal V1 plus V2, right? We start off with this. Then we substitute this formula, V equal IR, or V equal RI, okay, into this equation. Alright, okay, substitute inside here, so I get R times I equal to R, I will call the effective resistance R. I will call R1 and R2 the individual resistances. So R1 times I1 plus R2 times I2. Okay, I substitute V equal IR so I get RI times R1 plus R2 I2. Okay, but I is constant, right? So but I is constant. So what does that mean? I is equal to I1 is equal to I2, right? So what can you do with them? If I is 2, right, you get 2R equal to 2R1 plus 2R2. What can you do with the 2? You know what I'm saying? Huh? Yeah. Don't need factorize. Just cancel it. Okay? These three are the same. You cancel off. Understand or not? Cancel off. They're all the same. Okay? So I cancels off. Alright? Okay, so cancel out. Okay, so you cancel I out. What do you get? R is equal to R1 plus R2. Okay, that's where we get our equation 3. Okay? Equation 3 lah. Okay, equation 3. So this is where it came from. Sometimes, I mean, if you want to call effective resistance REFF, you can just write REFF. If not, you just write R equal R1 plus R2 is also fine. Okay? To be clear, you write REFF for effective resistance. Okay? Can? Alright, so this is where we get the third equation from. So this is where it came from. Alright? Any questions so far? So basically, how do we use this equation is that if I have a circuit, right, with three resistors, okay, say 2 ohms, 3 ohms, 5 ohms, for example, okay, the total effective resistance will be 2 plus 3 plus 5 equal 10 ohms. That's all. Very simple. Just add them up. Okay? For series circuit. Alright? Okay? Okay? Now for parallel, alright, okay, we start off with I equal to I1 plus I2. Okay? This one, the previous one, I just write from 2, okay, so that you know where it came from, alright? Okay, so now this one is from 1, the first equation for parallel circuit, alright? So I equal I1 plus I2, okay? Then we substitute V equal IR, I equal to V over R, okay? We want to get rid of the I, we want to introduce R inside here, okay? I equal V over R. So what do we get? Instead of I, we have V over R equal to V1 over R1 plus V2 over R2. You know what I'm doing? I replace I with V over R. That's all. So I becomes V over R, I1 becomes V1 over R1, and I2 becomes V2 over R2. Can? Okay? So, but what do you notice about V? V is constant, right? But V is constant, right? Okay, so what can you do when V is constant? Same thing that happens, okay? Cancel V, right? So here I cancel V, cancel because they're all the same, right? What do you get? So you get 1 over R equal to 1 over R1 plus 1 over R2. Right? So this is the equation 3 for the parallel circuit. This is where it came from. Any question? So basically what have I done? I have derived equation 3, right, for both series and parallel from the from V and I. I get the relationship for R. Okay? So V, I, and R for DC circuits, right? We are always talking about V, I, and R. Okay? We are not so concerned about the charges anymore. So you won't see Q, you won't see W, right? You only see V, I, and R. Okay? So we have already derived these equations. So now we know where they came from. Okay? But now how do we apply it, right? Which is Fiona's question. Okay? So how do we apply it? So let's look at one example here. Alright, so if we have, let's say, a resistor in parallel with another resistor, okay, let's say it's 3 ohms and 6 ohms over here. Alright, and then I ask you to find the effective resistance of this circuit. Okay, effective resistance, so 1 over R is equal to 1 over R1 plus 1 over R2. So 1 over R1 is 3 and 1 over R2 is 6. Okay, so 1 over R equal to 1/3 plus 1/6. 1/3 plus 1/6 is half. Okay, all right, if you use your calculator, you get half. So therefore, since 1 over R is half, therefore R effective resistance will be equal to, flip half, you get 2 ohms.